Okay, welcome. We have our third speaker, Iacopo Longo from Imperial College, London, and he'll be talking about tipping in EWS and some non-autonomous scalar ODEs. So without further ado, thank you again, Iacopo, for accepting our invitation, and go ahead.
Well, first of all, thank you, Emmanuel, and everybody for organizing this. It's really nice to be in such a inspiring series of talks on math and climate. Mine would be a talk rather on the first than on the latter, but I hope that that will be able also to convey a bit of motivation of why this is interesting for at least for theoretical climate science. So this is mostly work that I've done with Jesus Dueñas and Rafael Obaya from the University of Valladolid in Spain. The idea for today is that I'm going to start very slowly with a simple cartoon on what tipping is, just so we're all on the same page, and then understanding a little bit more about non-autonomous scalar ordinary differential equations and early warning signs for a tipping for a critical transition.
So, Iacopo, before you continue, there's one term that you did not explain in your title. What is EWS?
This early warning signs. So this is about, rather warning for incipient tipping point or critical transition.
Thank you. Thank you.
Thanks. Okay, so as for tipping, I'm going to start with this rate-induced tipping. I think it's the most common phenomenon, even in the literature. So I thought this would be the most or the easiest way to introduce the concept. And the idea is that typically you consider two different systems, autonomous systems that differ only on the value of a parameter, gamma minus and gamma plus, and also that are topologically equivalent. In fact, you also assume that there's a continuous branch connecting the attractors from this system from the value gamma minus to gamma plus, and there's no autonomous bifurcation happening. And then what you consider is a time-dependent variation of the parameter, so a function capital gamma that is asymptotically constant at gamma plus as t goes to plus infinity and gamma minus as t goes to minus infinity. And what one considers is rather the transition equation, which is x prime f of x capital gamma t. But now you have an explicit dependence on time, so that this is a non-autonomous problem. Now there's a new parameter here, which is this c called the rate. The larger c is, the smaller is the compact interval in which the biggest bunch of this transition will happen. But this whole transition will always take place on the whole real line between minus infinity and plus infinity. Now, as we will see, now this is done for rate, but it could be something else. It could be the size, it could be the phase, and we'll see a bit more of that in the next slides. Now, in practice, this is a bit as creating a connection between this system in the past at minus infinity for the value of the parameter gamma minus, and this system in the future for the value of the parameter gamma plus. Now, in the simplest case, these attractors are only hyperbolic equilibria, and one is concerned with the one unique solution that limits the hyperbolic attracting equilibrium in the past as t goes to minus infinity. This is a solution now, the transition equation, so the non-autonomous problem, that has a weaker form of attractivity that I will discuss a little later. So the important thing is about the future of this solution. Typically, when the rate is small, you can intuitively see that this transition equation is approximating a adiabatic transition, like a parametric transition between the value in the past and the value in the future. And so you'd expect to have a connection from the past to the future through this weakly attracting solution. But for some rates, for some problem, and when this rate grows, what happens is that this solution maybe blows up in finite time, or it ends up connecting somewhere else as t goes to plus infinity. So if this phenomenon is called tracking, this phenomenon is called tipping. And here, since the only parameter that is creating this different behavior is the rate, it's called rate-induced tipping. Of course, it could be any other feature on this transition of the parameter gamma. It could be the size, it could be the phase, once again, or something else. So later in the talk, I'm gonna just talk about tipping without specifying if it's for rate or for size. But the idea is the following. So just to make a point, this is something that in fact was introduced for something that is climate related. So the first notion of rate-induced tipping was by Victoria, Ashwin, Luke, and Cox for a carbon cycle model. And then there's been a few papers over the years. These are all quite old, if you want, at least 10 years old. And they deal with the rate-induced tipping for different climate elements. So I'm not going to talk about any of this in this talk. I'm not a specialist on climate science. So this is what I hope to learn from you somehow. But I want to talk about the mathematics behind it, and I'm trying to understand the characterization of this phenomenon in mathematical terms. Now, more importantly, for me, I don't deal with autonomous systems in the past and in the future, but with non-autonomous systems, both in the past and in the future. Meaning that even these systems here, in the past for gamma minus and gamma plus, they have an explicit dependence on time. So when you consider the transition equation, this has two dependencies on time, the inherent one, and the one that comes from the variation of the parameter. As an example, in climate, maybe you can assume, okay, you have your own original system that has astronomical forcing, Milankovitch cycles of some sense, maybe deterministic or even random or chaotic. And then you have a time-dependent variation of the parameter, maybe growth of emissions since the Industrial Revolution, or some growth in albedo, if you want. Now, for my talk, actually, I'm going to talk about scalar problems, which is the simplest case. But unlike the autonomous one, is already rather complicated. So in fact, an attractor for a non-autonomous scalar problem doesn't need to be an equilibrium, doesn't need to be a stationary solution, can be in fact a very complicated set, even with fractal structure. You're going to stay in the simpler case of one trajectory, hyperbolic, which I will explain what it means, but not necessarily stationary. So it can just move and do whatever is needed. So the transition equation, both the past problem, the transition equation, and the future problem, they live on the same real line, of course. So in fact, you could extend these attractors over the whole real line. Again, for tipping, what we are concerned with is the behavior of the solution, the unique solution from the transition equation that at minus infinity limits at the attractor of the past problem, and see what its future. What is its future? Either it connects to the attractor plus infinity, what we will call tracking, or it collapses at some point, which is the tipping scenario. Okay, now getting a bit more mathematical, in downward setup, the vector field is going to be smooth enough, typically uniformly continuous and bounded on compact subset of the phase space. And this function gamma here that represents the variation of the parameter is going to be simply a continuous function, which is asymptotically constant. Okay. All right. One more thing is that we're not going to study general problems, but we're going to have a bit more of assumptions, which is concavity or d-concavity. D-concavity means concavity of the first derivative of f. So now I'm going to slowly show what the assumptions are for the problems that we consider, and I'm going to explain all of them a bit in detail. So the first one is about regularity. So besides continuity, we're going to assume that in the concave case, we also have that the function is differentiable, and the first derivative in x and both f are bounded and uniformly continuous on compact subset of the phase space and on the parameter space. For the d-concave case, same thing, but we're going to add another degree of regularity. So instead of C1, we're going to go to C2, because as we said, we study concavity of the derivative of f. Okay, second assumption is basically about the behavior of the vector field when x is large. So in the concave case, it means that if x is large, either positive or negative, then the vector field is pointing downwards. Imagine a polynomial degree 2. Okay. So this is called coercivity, by the way. For the concavity, d-concavity, this is dissipativity. When x is large and positive, then the vector field is pointing downwards. And when x is large and negative, then the vector field is pointing upwards, so that it's creating an invariant set somewhere in the middle. Now concavity, yeah, here expressed in terms of the first derivative. If we had second derivative, this we would just ask that the second derivative is negative. D-concavity, exactly the same, but for the first derivative. Nothing strange. And finally, something about the structure of the limit, the problem in the past and in the future. So we're going to assume that the concave problem has exactly two hyperbolic solutions, one attracting and one repelling, both for the past and for the future. And the d-concave problem has exactly three hyperbolic solutions, two are attracting and one repelling. We will see that this is very natural, and this is actually the only case that can happen if there are the maximum number of hyperbolic solutions for these two types of problems. Now, this seems rather technical, but in fact, I want to show a couple of examples of problems that actually use this in theoretical ecology. So, for example, for concave problems, you have a couple of models for population dynamics, and d-concave, similar problems with Ali effect multiplicative, for example. So you see that typically polynomials of degree 2 or polynomials of degree 3 are respective examples of concave and d-concave problems. So very natural. Maybe more interesting for this audience is this kind of zero-dimensional locally concave climate models a la Gill-Boudico-Sellers, where you have a black body radiation and a solar irradiance. Well, now we're assuming a time dependence either on the solar irradiance or the emissivity coefficient. So incidentally, this is something we're working on now with Rafael Obaya and Anna Sanz, also in Valladolid, in terms of averaging what is the behavior with respect to the autonomous system and what is the impact of that on climate sensitivity. And hopefully this is something that I'll be able to talk about later in the year. So we're hoping to submit by the end of the year. Hopefully we can talk about that in a few months. Okay, so now we leave the examples behind, and what I'm going to try to convince you is that one can characterize very neatly the dynamical scenarios for these kind of problems. The way we do it is by identifying three different scenarios. So case A is if we have bounded and hyperbolic solutions. Now, hyperbolic in this non-autonomous setting is a generalization of a hyperbolic equilibria of autonomous systems, meaning that they are non-stationary solutions in general that attract exponentially solutions which are nearby, either in forward time if they're attracting, or in backward time if they're repelling, or possibly saddle cases. Mathematically, this we write it in terms of the solution of the variational equation calculated along a certain bounded solution B tilde of the nonlinear problem. If this transition or evolution operator of the linear problem, the linearization, decays exponentially, either in forward time or in backward time, then we call the solution B hyperbolic. Okay. So case A is existence of bounded hyperbolic solutions. Case B is existence of bounded solutions, but no hyperbolic ones. And case C is no bounded solutions whatsoever. Now, clearly, these three cases are possible for every differential equation, not just for concave or d-concave. But at least in the concave case, we can say a bit more. So when we look at these three cases, in particular for a concave problem, we can have at most two hyperbolic solutions. Exactly, in fact, if we have a hyperbolic solution, there are exactly two. One is attracting, one is repelling. So this is exactly the generalization of a quadratic polynomial autonomous, where if we have hyperbolic equilibria, then there are exactly two. One is attracting, one is repelling, and the only bounded solutions are in between. The only difference is that, of course, now they don't need to be stationary. Moreover, in the case of the transition equation, we have that if we have these two hyperbolic solutions, they are in fact connecting the attractor-repeller pairs of the past and of the future. So this is the tracking scenario. Case B is the existence of bounded but non-hyperbolic solutions. In general, in the non-autonomous case, this can be very complicated. So there can be an infinity of bounded solutions which are non-hyperbolic with this fractal structure. It's almost automorphic dynamics. But for the transition equation, this is not possible under the assumption that we have given. So if there are bounded solutions that are non-hyperbolic, then there's exactly one. And this as a weaker form of attractivity and repulsivity. So the analogous of the autonomous, let's say, quadratic equation. And case C, as we said, it's the no bounded solutions case. So if we look at pictures, it looks a bit like this. Here we have, you see the attractor in red, the repeller in blue. The bounded solutions are only the ones in between, and every other solution is unbounded. In the case B, which is a bit the critical case, these two solutions are colliding. Yeah, so we have a one unique bounded solution, which is non-hyperbolic. And in fact, if you start back in time, you see that solution try to approximate this bounded solution. But since this is also repelling, the solutions are eventually going to go away from it. So this one unique bounded solution is connecting the attractor of the past to the repeller of the future. It's a bit of a heteroclinic connection in some sense between the problem in the past and the problem in the future. So this strange form of weak attractivity is called pullback attractivity. It's something really special and specific about non-autonomous system that doesn't exist, or at least is non-distinguishable in the autonomous case. It's attractor in forward sense, it's attractivity in forward sense, but not from the present to the future, but rather from the past towards the present. Okay. Now we have all these are the possible dynamical scenarios for this kind of equation. We put a parameter here and we do a study of bifurcation. An important result is that there's exactly one value, critical value mu star, that discriminates among these cases. So in particular, if you are exactly at mu star, then you have the critical case. If you are above the critical value, then you have the two hyperbolic solutions. If you are below, then you have no bounded solution. So for this reason, this is what we call a non-autonomous pattern of saddle node bifurcation, because two hyperbolic solutions collide at a critical value, which is unique, and then no bounded solutions exist anymore. Now it's interesting because in the autonomous case, this everybody can prove basically in few lines. But in the non-autonomous case, this is incredibly complicated. So you can look at this paper here in 2023. It takes almost 10 pages to prove, first of all, that you have only two hyperbolic solutions, and then that the only bifurcation scenario is exactly this non-autonomous saddle node bifurcation. Importantly, what this proves for this class of concave problem is that any form of tipping you may have cannot be anything but the non-autonomous saddle node bifurcation. Okay. D-concave case, similar, a little more complicated. This is something that Dueñas, Núñez, and Obaya studied in 2023. Even here, you have three cases that are slightly different. Case A is the existence of exactly three hyperbolic solutions. Two attractive and one repelling is the case that you see here in the middle. They connect for the transition equation the attractors from the past to the attractor in the future, so you have tracking. Case B is existence of two bounded solutions separated, only two uniformly separated bounded solutions. One needs to be hyperbolic, either in this case here in red, or in this case here in red, whereas the other one is non-hyperbolic and has this weak form of attractivity, this pullback attractivity. And case C is the existence of one unique bounded solution, and it needs to be necessarily attractive. So in this case, what you see in terms of bifurcation, again, when you do this parameter variation, is that there's, again, just exactly two critical values, mu plus and mu minus. Each one of them corresponds to a non-autonomous southern node bifurcation. So in terms of the analogous autonomous version of the bifurcation diagram, you would see this famous S with this double southern node bifurcation. For a certain parameter of the value of the parameter, you have both attracting solution, and then if you go one side or the other side, you have a collision and you're left with only one hyperbolic attracting solution. Okay, so this tells us a lot about what a tipping can be for this class of equations and the respective models. And at this point, let me say, the problem is that practically finding these bifurcation points is really hard. It's not like in the autonomous case where you can compute it explicitly. Here, you're talking about a collision of globally defined solution from -infinity to +infinity, which you can also never check numerically. Plus the fact that after the bifurcation, you lose this attractivity. You only have this pullback attractivity, which is not forward attracting. In fact, we know that it's repelling in forward time. So you never know when you're simulating in finite time if you're approximating well this pullback attractor. So these are very delicate problems for which you cannot compute explicitly the tipping point. Now, we believe the numerics. I think we do. But the idea is to find a bit more of a rigorous method to assess how close we are to these bifurcations, and so the tipping points for the models. So the idea to use finite-time Lyapunov exponents as early warning signs for the bifurcation. I'm going to do a slight brief recap about Lyapunov exponents first, talking about the autonomous systems. Now, for the autonomous systems, when we have an ergodic measure, we use the Osladek theorem to have to guarantee the existence of Lyapunov exponents. So typically, that these limits of 1/t logarithm of stuff is well defined and it converges to something. But now we have a non-autonomous problem, right? So before applying this theorem, one needs to construct an autonomous flow so that this can be done. Now, there's a classic way of doing that we learn in analysis. We augment the phase space with an additional variable, t prime equal to 1. This is an autonomous system, but unfortunately is a very ill-posed autonomous system because this additional variable always makes everything non-compact. So we cannot apply autonomous dynamical system theory to this system because there's nothing compact. Everything is blowing up. And in fact, even the Osladek theorem in this sense would not give us anything interesting. But there is a smarter way of doing that, which is instead of augmenting the phase space with t prime equal to 1, so the real line basically, we augment the phase space with a functional base where we label time in terms of the shifts of our vector field. So the time translation of our vector field are representing now time. Instead of writing time s, we consider the time shift, the time s of the non-autonomous vector field. Now this is a smarter option because if we put all these time shifts together, plus their limits as t goes to plus and minus infinity, under suitable topology, this gives us a compact metric space. So this is what's called the Hull construction and the skew product formalism. So we're ending up having a flow that is made of the solution, made of two components, the solution and the time translation of our vector field that works as a labeling of time. So instead of a real line, now we have a functional space in the base. This is very important, very interesting, because immediately this Krylov-Bogulyobov theorem, for example, gives us the existence of an invariant measure on the base, because we know that it's a compact metric space. So now we can also try to apply the Osladek theorem, and in particular, if we have hyperbolic solutions, then for an ergodic measure that is basically supported on these hyperbolic solutions, we can calculate explicitly the Lyapunov exponents using the variational equation along that hyperbolic solution. And what's more, we can use Birkhoff ergodic theorem, so the additive ergodic theorem, to substitute the time average to the average on the hull, which is this labeling of time that we have done. So this is very effective, and it's very smart, and it's very convenient. It gives us a rigorous and sustainable way to do Lyapunov exponents for non-autonomous systems. Okay. So what happens now for our transition equation? Let's say the transition equation clearly does not affect the past or the future. And we have assumed that both the past and the future, they have their own attractor-repeller pairs of hyperbolic solutions. So the Lyapunov exponents of the past attractor-repeller pair and the future attractor-repeller pair, they are not affected by the transition equation. So what happens is that when we look at the Lyapunov exponents of our transition equation, we'll see that anytime we have an attractor-repeller pair connecting the past to the future, then the Lyapunov exponents for the hyperbolic attracting solution will be strictly negative, and the Lyapunov exponent for the hyperbolic repelling solution will be strictly positive. And this will always be so, even very close to the bifurcation. Because the tails of this integral are much more important than what happens on a compact interval. So the effect of the past and the future on the Lyapunov exponents in this integral are much more relevant and keep always the Lyapunov exponent either positive or negative. So this means that in practice, this non-autonomous sudden bifurcation is a bit of a discontinuous bifurcation, because even at any point before the bifurcation, the Lyapunov exponents of the two solutions will stay respectively negative and positive. They will not approach each other. They will not go to zero. But something else happens, of course, and this is infinite time, because we know that in finite time, at the critical case, we have a unique bounded solution which is connecting the attractor of the past to the repeller of the future. So the idea is rather to use finite time Lyapunov exponents, which we now define in this way as backward finite time, simply as a choice because we assume to know the past but not the future. So we're going to use a averaging, or let's say an integrating interval in the past of a certain length t, capital T, where we're going to approximate the Lyapunov exponent. Okay, this is our definition. We're going to do it for the attractor in particular because we assume that the attractor somehow encapsulates the state of the system where we are now. So we can somehow, we have data about the past, we know where it was, and we can compute things explicitly. We need to calibrate this, and we need to understand what is a reasonable value for this capital T, for the length of the integral, of the interval where we integrate and we calculate our finite time Lyapunov exponent. How do we do that? So the observation is that if we fix ourselves at the critical value, then integrating on growing intervals, so on a interval on a window which has a length which is sufficiently big, and plus situated in the future, it will be approximating the Lyapunov exponent of the repeller of the future, and therefore will be positive. On the other hand, if we consider a window which is large enough but situated in the past, this will be approximating the attractor, the Lyapunov exponent of the attractor in the past, and therefore it will be negative. So we need a length of the window where we do this integration large enough to capture the behavior in the past of the future of the attractor and the repeller, respectively, so that we are reasonably sure that we are doing something correct. Moreover, this tells us that in the critical case, since we are passing from a negative sign to a positive sign, this Lyapunov exponent here will change sign. So we'll get to zero. Okay, so this is interesting for the critical case, but as we said, we never know really when this critical case happens. we're not able to approximate it numerically correctly. So this information is not very relevant if we just stay in the critical case. But fortunately, now we can use continuous variation of solutions, and we'll know immediately, we can prove it rigorously, that the finite-time Lyapunov exponent will change sign over time, even close to the critical case, even without arriving to the critical case. So here I make an example. So you see here is this is an Ali model somehow with the multiplicative Ali effect, plus a time-dependent variation of a certain parameter multiplying a certain immigration term in some sense. What you see here is in blue the finite-time Lyapunov exponent computed for different length of the interval. So capital T goes from 25 to 100. And this is reasonably close to the critical value. So you see that, in fact, this finite-time Lyapunov exponent changes sign. What you see in dashed line in red is the Lyapunov exponent of the past attracting hyperbolic solution, which is, of course, a constant value. And the solid lines are percentiles of this value. So either, I don't remember exactly, it must be maybe 0.7 and 0.5 of the value of the Lyapunov exponent of the past attracting hyperbolic solution. So here you see that there is a trade, because the larger the window is, the closer you need to be to the bifurcation, to the critical value, before you see a change of sign in the finite-time Lyapunov exponents. But on the other hand, we want that this window is large enough so that we can approximate well at least the behavior in the past and in the future as a guarantee of doing things reasonably well. That's why we use this percentile somehow, in sense that maybe even an overgrowth past, say, 0.5 of the value of the Lyapunov exponent of the past can be considered as a triggering signal. Okay, this is the calibration we need to do, and this is what I just explained before. How do we apply this? Instead of doing rate-induced tipping, here we did it on some rate-induced tracking. This is what we called. This is including this phenomenon of overshooting, which was studied by Paul Ricci and collaborators very well. So they introduced this idea. And again, with our model, the idea is just to use a pulse of this parameter variation that is exploring a region of the parameters where we have a collapse of our system. The idea being is that if we do this exploration of this dangerous region of the parameter space quick enough, we are able to maintain, to recover our desirable state. So for example, you can imagine, I don't know if this makes sense, that this upper attractor represents your interglacial temperature, atmospheric temperature for a certain zero-dimensional climate model. And what you see here is your glacial, for example, state. Okay, this is of course not the case, but it's a different, completely different model, but just so you have an idea. So, for example, this would be the case where you have a growth in albedo. If this growth of albedo is fast enough, even if it's exploring a dangerous region, dangerous values where we would go into glaciations, if this happens only on a restricted amount of time, we hope that we're going to be able to remain in our interglacial state. So this is in fact what you see. And here you see that for higher values of the rates, you're able to remain in your desirable state. Whereas if your exploration of the dangerous part of the phase space is too slow, you end up having a collapse towards this undesirable state, for example. So this is what the finite-time Lyapunov exponents do for each one of these cases for different rates. And I think, if I remember well, this is done for a capital T of 50. And you see that you have an overgrowth past this threshold of 0.5, the value of the Lyapunov exponent of the attractor of the past. Eventually also a change of sign, again an overgrowth when this is already beyond the tipping point. So in practical terms, this is telling us that finite-time Lyapunov exponents calculated exactly along this one specific solution can be used as an early warning sign, even though Lyapunov exponents for these models cannot be used because they would lead to a discontinuous bifurcation. So they would not signal any approaching bifurcation. So now, okay, you can just get a little more hungrier in a way and say, okay, I'm going to do something stranger, which is instead of considering this rate, I'm going to consider a time-dependent changing rate, which is asymptotically constant. So you get asymptotically constant rate in the past and in the future, and you try to explore if these cases are still covered by finite-time Lyapunov exponents as early warning sign, and this is in fact the case. Yeah, you see a change of the sign, or at least an overgrowth and then a change of sign if you are reasonably close to the bifurcation value. So I maybe don't go into the details of this, so because I think I am already at my limit time, but let me say these are the conclusions. What I try to show in this talk is that you can characterize rigorously and explicitly the dynamical scenarios for this class of scalar differential equations, concave and d-concave. We have shown that for the transition equations, all can happen in terms of tipping, no matter if it's for rate, for size, for phase, or any other crazy phenomenon you can come up with. It is always a non-autonomous sudden node bifurcation. And then we have discussed the use of this finite-time Lyapunov exponents as early warning sign to understand how close we are to this bifurcation scenario. This is the paper that I've talked about in this presentation. Nonetheless, these are also the rest of the papers that I've worked on with several collaborators in the past couple of years about tipping. Again, our approach to tipping is through non-autonomous bifurcation theory, and we're trying overall just to understand this phenomena in a way that is rigorous and is generalizing the autonomous bifurcation theory. These are the people that paid for this work, so I'm going to thank them, but then above all, I'm going to thank you for your attention and for being here. Any question you may have, I'm very happy to answer. Thank you.
All right. Thank you, Iacopo. Let's thank the speaker. At this time, we open the floor for questions. Are there any questions for Iacopo?
Let me give back here if somebody is interested.
Okay. Okay, so we have one. We have James.
Yeah, so I'm curious. First, thank you for a great talk. So this concavity condition, is it something? I mean, you mentioned the analogy like with quadratic polynomial, but is there some obvious reason why that's the kind of sufficient to give these tipping phenomena?
Right. Well, I mean, this is one of the cases in which we can explain the tipping phenomenon through a sudden node bifurcation, which we believe is the basic ingredient to get this sort of tipping scenarios, a collision between a stable and unstable object, although non-autonomous. So the same way as in the autonomous case, where the easiest problem where you can get this collision is the concave, at least at first the quadratic polynomial, and then concave problems. This is what we started to investigate. And it's really hard. It's really hard. So this was the way to go somehow. This is where we would expect that things would go well. Of course, there's much more to study and many more cases that are not included. And this is what hopefully we'll do in the next years.
Thank you.
Okay, are there any other questions? Feel free to speak. So Iacopo, I have a few questions for you, if you don't mind.
Yes, absolutely.
Okay, so I mean, so when you did your examples, for example, on slide 23,
yeah,
you had gamma is gamma c sub t, right? So there, c was like acting like a ramp. Is that correct for this kind of
this is a rate, yes.
Okay.
This is a rate where this gamma, what it's doing is what is shown in this picture. So it's a pulse. It's a pulse that is visiting a region of the parameter space where you would have a tipping.
Okay, so then I want to differentiate that with your mu, right? With the parameters. So when you had this non-autonomous system where you had x prime equals f plus mu, and then you had this mu critical. So you had the case A, where you had the bounded hyperbolic solutions. You had case B, where you had bounded non-hyperbolic, and case C, when you had no hyperbolic. And then you were looking at this mu critical, right? So then,
Yes.
okay.
So apologies for the this is a abuse of notation. This is not the same mu. Okay. So what you have here is just a coefficient, a time-dependent coefficient that here represents certain threshold of the LE effect. What you have on the other hand in this slides here,
it's a parameter.
It's a parameter. It's a constant you get. This is a it's a critical value as you would get it in a autonomous bifurcation. In a normal form, you could calculate a certain value of the parameter is the one that gives you the Southern law bifurcation. Problem is that here we cannot compute it explicitly, but what we can prove is that it does exist.
Okay.
Yeah, so they're not the same thing.
No, for sure. But I just wanted to differentiate between like a bifurcation induced effect and then a ramp induced effect. So in this case, you have like you're relying on the parameter, whereas in your examples, you are relying on this C. Yes or no?
So the C here would be included somehow in this gamma.
Okay.
I'm not writing it explicitly, but it would be here somewhere. This is gamma of CT. Depending on the gamma,
it is there.
It could be there. I want to keep it more general, saying it could be the ramp, it could be a size, it could be a phase, it could be anything that generates your tipping. So if you want, you could call this a gamma sub-index C, where you have a certain parameter. Maybe it's the rate, maybe it's the phase, whatever it is, that if changed can produce a certain a tipping point, so a bifurcation.
So okay, what I wanted to clarify is when you say rate induced tipping, is it because the system is non-autonomous? Is this what you're relying on? Or
when I say explicitly rate induced tipping is because I'm multiplying a C here.
Okay. So okay.
So I'm using the rate as the parameter leading to the tipping point. Here, all I'm concerned with is a time-dependent variation of the parameter. I'm saying some of them give you a tracking scenario. Some of them give you a tipping scenario. I'm not telling you exactly what is it that is generating. If I take now a family, parametric family, this could produce one case or the other.
Okay.
I don't know if this, yeah.
Yeah, I mean, okay, it's a little bit clearer. So another follow-up questions, unless anybody else has. Okay, so then when you had your construction of the autonomous flow with compact base, you mentioned discontinuous bifurcation, right? Can you elaborate on that a little bit more? Like, what do you mean?
Right. The only thing, so what happens is that here you have a transition equation, but you have also a problem in the past and a problem in the future, right? Now imagine you're trying to calculate the Lyapunov exponent on this hyperbolic attracting solution, and you do it only on the negative half line. So what happens is that this is going to approximate the value of the Lyapunov exponent of the attractor in the past. because for a very heavy infinite half line, these two solutions, the hyperbolic attracting of the transition equation and the hyperbolic attracting of the path problem, they're very close. So what is going to end up be is that basically you're going to always have a negative value because you're integrating on an infinite interval. Now, same thing if you do it for the hyperbolic repelling solution, which is connecting to the repeller in the past or in the future. So if you, for example, you do this calculation of the Lyapunov exponents on a negative half line, again, what you left is that it's going to approximate the repeller of the past. And therefore, the Lyapunov exponent of this hyperbolic solution here is going to approximate the Lyapunov exponent of the repeller in the past. Consequently, since the past is not changed by this transition, irrespectively of what happens here, if you have the collision or not, up to the last moment, you still have connection. And therefore, your Lyapunov exponents will remain respectively negative and positive. So they will not approach each other at the bifurcation value. So in this sense, we call it discontinuous, meaning that the Lyapunov exponents of these two solutions will respectively stay negative and positive. And then discontinuously, you have the bifurcation. They're not approaching zero symmetrically.
All right. Thank you so much for explaining all of that. Okay, so are there any other questions for the speaker?
There was something in the chat, but I don't know if it's questions or not.
There's
No.
people saying that they're heading out.
Okay.
But okay. All right, let's thank Iacopo one last time, and thank you so much for a wonderful talk.
Thank you very much for having me. See you soon, hopefully.